And so before starting today's class, I will briefly explain about the second lab. So I believe the notification was sent to you, right? So I posted the second lab on Blackboard. And then actually I believe you can quickly complete this lab if you already complete the first lab. Okay, so if you successfully uh, build the cross-compile toolchain on your Ubuntu or on your virtual machine, then I believe you can easily. So actually, you can follow instructions in this second lab. Okay, so actually, in the previous class, we learned about the function calls, right? And then we learned the RISC-V instructions that can support the function call, right? So actually, in this second lab, so you will be requested to compile the simple function code. So actually, as you can see, so this is the code you need to compile using the RISC-V compiler. If you see that this code, you can find the main function here. Okay, so this the first function is the main function, and then I already explained that when a C code is executed, so actually the compiled C code is executed. So firstly, the main function is called. Okay, the main function is called. So which means that we need to jump to the main function. Also inside the main function, you can find the function call here. Okay, which function is called fact iter. So this is the iteration version of factorial. Okay, so you can find the iteration version of factorial function here. Okay, so simply the main function calls this fact iter function, and then as you can see, we use the n as an argument for this function call. Okay, so n is delivered to the fact iter function, and then as you can see, the n is the 8. So in this lab, so you need to compile this C code using the RISC-V cross compiler. So we use the RISC-V 32 unknown ELF GCC. So this is the 32-bit version of RISC-V cross compiler. Also, you need to set the proper options, compiling options like here. And then, as you can see, so this is the different option. So actually, in the first lab, so we used just RISC-V. So this is the base version of the 32-bit RISC-V instruction set. But for this lab, we use the RISC-V-IM. So M represents multiplication. Okay. So actually, in the previous class, we learned that RISC-V is the RISC-V includes several extensions, and then we can use M extension for integer multiplication and divide instructions. So which means that if we use M extension, then we can use RISC-V multiplication and division instructions. So why do we need to use multiplication? Because this is the factorial. So C code includes multiplication, right? So that's why we need to use the RISC-V-IM. So if you do not use this RISC-V-IM, then the compiler will call another function. So this another function implements the multiplication using integer add operations. Okay. So So in order to use the BOR instructions, the multiplication instruction, you need to use the alpha equal to IM. Okay, so you need to remember this, and then as you can see, we can generate the disassembled dump file. Okay, then we can simulate the execution of RISC-V instructions using Spike ISA simulator. Okay, Spike RISC-V ISA simulator. Okay, so you can use the help command inside of the Spike simulator. Okay, and you can find the several instructions. So actually, you can follow these instructions here in the document, and also we can generate the command script. Okay, script is the group of commands, and then we can use this script file for automatic execution of Spike simulator. Okay, so this is the content of the script. So the script name is the fact_iter.cmd. It means the command. Okay, and then okay, so we can execute Spike simulator using this script, command script. Okay, then these commands are automatically given to the Spike simulator, and then Spike simulator will generate the log file. Okay, so this is the output of Spike simulator. Okay, so actually, if you follow these instructions in the document, you can find how many instructions are executed after the code, after the function call. Okay, so so if you execute these Spike commands, then we can get instructions. We can get executed instructions after the function call. So it means that the executed instructions between a function call and return from the function. Okay. So actually, if you use the dump file, then actually inside of the main function you can find the JAL. So we actually in the previous class we learned for the function call we can use JAL, and then actually I did not include the fact item function here, but we can find the RET. It means the return. Okay, we can find RET instruction at the last line of the fact underline item function. So it means that so if this RET is executed, then the function is complete, and then we can return from the function call. Okay, and return to the main function. Okay, it's a parent function of the fact underline item. So I recommend you try to understand this command. So actually, I also provide the dump file actually for this first instructions, the first practice. So actually, I also provide the dump file and this command script. Okay, but actually you can find the many PC addresses here. Okay, and then I set this PC addresses based on the generated dump file. Okay, so actually we need to figure out the PC of the is PC of the is function call. It means the JAL. Also, we need to figure out the very next PC, the PC of the very next instruction. So in this case, the very next instruction is the SW. Then you can get the PC of the next instruction is the 10094, right? So actually, you can find the PC here and then PC here. So it means that we just go to the program counter, the address of JAL here, okay, JAL, using this command, and then it means that we can jump to the SW. It's the very next instruction. And then actually, if we use this until end command, then executed instructions are displayed. And then this displayed instructions are returned to the log file. Okay? So we can get the number of instructions. If we count the number of lines in the log file. Okay. So if you read this lab document, then I believe you can easily understand what I said. Okay. So this is the second lab. And then also you can practice the same flow using the recursive version of factorial function. Okay, and then you can compare how many instructions are executed by this recursive version of factorial function. Okay, then actually, so in this example, so we can get the 99 instructions executed when this function is called by main function. Okay, and how about the recursive version? Now, you can follow the instructions here. Okay. Now I believe so. Actually, I believe you can complete this lab very quickly. Okay. So if you build this RISC-V tool chain environment correctly, the first lab. Okay. Any question? Any questions regarding the second lab? No? Okay. Good. So, okay. Okay. So in the previous class, we learned, as I mentioned, we learned RISC-V instructions that can support a function call and return from the function, right? And then actually we learned about how the recursive functions are implemented in RISC-V assembly instruction, right? So and then also we learned how the stack memory space is managed by this recursive function call. Okay, and then actually it's the same. So actually when the function is called, then we need to use the JAL, right? And then which means that the return address is stored in RA, because you need to remember that when a function is called, then we need to return to this called position, right? So which means that when a function execution of a function is complete, then we need to return to the next instruction. So which means we need to store this program counter, that is the address of next instruction in RA, right? That is what we learned in the previous class. The recursive function is the same. So which means that we need to also store RA. But because the recursive function will call is the same function again, then RA is stored in the temporary memory space called stack. So which means that we need to also manage the stack pointer. And then actually when every function is called, then actually the stack space is assigned. Then the required data need to be stored in the stack. And then the function is, and then if we return from the function, the stack pointer is restored. Okay. And then, but actually in the class, so we just learn the stack space is allocated only for the required data. Okay, so this is quite optimized. Okay, but if you see the generated code like here, actually, so I did not include the generated code here, but you can find that actually in reality the stack size is the letter larger than the minimum size, minimum required size, because actually when the instructions are compiled, so which means the RISC-V instructions are generated from the high-level code, then some data like this variable data is also stored in the stack. Okay, because this data is not global data. This data is not a global data. So actually the local data inside the function are also stored in stack. So that's why the stack space is larger than this example. Okay, so if you generate this recursive version of the factorial function, so it's the same. I use the same code. Okay, so for the second lab. Okay? So, but the stack size is different. Okay, is it because the local variables are also stored in stack? Okay, so the code is a little bit different. Okay, and then I also actually I quickly went through this slide because we don't have enough time. We did not have enough time. So, but I believe you can easily understand how stack spaces are managed by each function code. Okay. So this is because stack pointer. So actually, before the stack space is updated, then we just observe the stack pointer. Then based on the stack pointer, we just store the required data in stack. Okay. So if you see this stack point adjustment, then we can also figure out how large. So actually, the word space, how many word spaces are allocated in stack. Okay, so the function is called, the stack is increased, it means the stack pointer is decreased, the stack size is increased because the stack pointer grows to the negative direction, right? And in this direction, so the stack size is increased, and then after the function is completed, then the stack is decreased to this direction. Okay. So these are what we learned in the previous class. Then, so now, we learn about the pseudo instructions. Actually, the pseudo instruction. What is pseudo mean? It's not real, okay? So it's kind of fake. The fake instruction, but we can use this fake instruction frequently. It's not a real instruction, but we can use these pseudo instructions in the RISC-V assembly. But these pseudo instructions will be translated into real instructions. Okay, so let's see the example. Okay, so assembler converts pseudo instructions to real RISC-V instructions. So we can use these pseudo instructions, but and then when these instructions are translated into machine code, then the assembler generate the real instructions, and then the machine codes are generated based on real instructions. So let's see the example. So RET, lowercase r. So for example, this is the pseudo instruction, and then if you see the generated RISC-V assembly code from the binary code, so we can generate the disassembled dump file, right? And then in the disassembled dump file, we can observe RISC-V assembly code, right? And then actually you can find the RET, it means return. So it is actually same to the return statement in C, okay? And then it means it is RET in RISC-V. But RET just same to the JALR 0 and RA and 0. Okay, so what does that mean? So what is JALR? So JALR for PC is become the RA plus 0, right? The data is stored in RA, and then the offset is added to the is RA value, and then it becomes the PC. And then the return address, the next PC is stored in is 0. So it's a new return address. But the 0 is always 0, so it will not be updated. Okay. So return is just means that the array is not updated. So because the destination register is not updated, but it reads the stored address, the stored return address from RA, and then it jumps to the stored return address. So it's the same to return statement in C. So which means that RISC-V assembly code, you can use RET instead of this instruction. But RISC-V assembler just change this RET instruction to this instruction, right? And then the machine code, like the machine instruction, is composed of zeros and ones. The machine codes are generated based on this instruction. Okay. So you can find the J is a simple jump instruction frequently. So this simple jump instruction is actually JAL 0 immediate. So return address is not stored because it is stored in 0, but 0 is not updated. So return address is not stored in RA. So it is a J immediate. And J, if we use the JAL and then immediate, it's a target of the jump. It's actually equivalent to JAL RA immediate. So these are pseudo instructions, right? So actually the right side instructions are real instructions. Then left side instructions are pseudo instructions. Okay, and pseudo instructions are translated into real instructions. Okay, and then how about the label? We also frequently observe labels, right? So these are labels. Okay, So in the dump file, you can find the labels here. And then also if we use see the generated assembly code. So if we use the minus uppercase S option from the RISC-V compiler, then we can generate assembly code from the C code. You can find the many labels. So label indicates where to jump. So actually the label is just a program counter of the instruction. So this is the example. So this is main. Main is the label, right? And then, but this label is just nothing. So it just represents the program counter. So this is the program counter of JAL. So if you find the label here, so this main represents the program counter of actually JAL. Okay, label is just represent the program counter of the is corresponding instruction. Okay, then how about this one? So you can find the JAL instruction here, and then it jumps to simple. And then where is the simple? Simple is here. Okay, so it means that if this JAL is executed, then PC will be labeled is simple, and then simple represents the program counter of JALR. So this instruction. So this is the 0x51C. Okay, then but this is just a text. It's not a real data, right? So this text data, this is just a label. This text data needs to be translated into real data, actually. Okay, so we already learned that when JAL. So the format of JAL is the RD. So this is the destination register and immediate, right? And then this immediate is the 2's complement number, right? Which means that actually this label simple needs to be translated into immediate number. Which number? So this is the example. So we use the immediate number here, and then actually this immediate number is the 0x51C. It is the simple, right? The simple, and then simple minus F. Okay, so 0x300. What is 300? 300 is the program counter of this JAL. So it means that this 300 is the PC of own instruction. So which means it's a executed jump instruction. Okay. So actually immediate is the 51C minus the current PC, the 300. So it is equivalent to 21C. You understand? So actually this instruction is equivalent to JAL, RA, and 21C. It's a hexadecimal format. Okay, so because we learned JAL format is the JAL and destination register and immediate. So immediate number is 0x21C. Okay. So actually, this label simple is translated into the immediate number. Okay? And then immediate must be multiple of 2. So we will learn why the immediate must be multiple of 2 later. So it should be translated into the machine code, but when this JAL is translated into the machine code, actually the last immediate bit is removed. So actually it is because, the size of a normal instruction is 4 bytes, right? And then also the RISC-V supports the small size instruction. So it's a reduced size instruction. And then the size of this reduced size instruction is 2. Okay, so because the minimum size of instruction is 2, then so the immediate must be multiple of 2 because the minimum size is 2. Okay, that's obvious, right? And then long jump. Problem of JAL is that JAL is the 12-bit immediate. No. JAL is the 20-bit immediate number. So which means that the maximum value is this is the around the -2 to 19 to the power of 19 to 10 minus 1. Okay. And then if we use the JALR, then we can use the 12-bit immediate number. So it is the signed number. But sometimes we need long jump. So which means that the immediate, when we use the jump instruction, then we the size of immediate number can be larger than the 20. Okay? So actually the hardware also needs to support this case. So in order to support this case, the RISC-V also supports the AUIPC command. Okay, so AUIPC command instead is the RD. So that is the destination, and then this is the immediate. So this immediate number is the 20-bit immediate number. But like the LUI, so we learned about the LUI, right? So when the LUI is executed, then we can use the 20-bit immediate number. But this 20-bit immediate number is assigned to the upper 20-bit of the 32-bit register, right? So it means that using the LUI, we can generate the 32-bit constant in the register. And then in the same way, if we use the AUIPC, so this is the new instruction, and then this is the destination register, and then we can use the 20-bit immediate number, then this is the result of the AUIPC. So it means RD is the current program counter plus 20-bit immediate, but this 20-bit immediate number is assigned to upper 20-bit of the 32-bit number, 32-bit data. So using the AUIPC, then we can set the 32-bit immediate offset for the jump instruction. This is the example. So AUIPC, RA, and 20-bit immediate. So it just calculate the RA equal PC plus immediate, but this immediate occupies the upper 20-bit, and then using the JALR, then we can just use the lower 12-bit immediate. Okay, so like the LUI, so we can use LUI and add I for generating 32-bit constant number. And then like AUI, using AUIPC and JALR, we can generate the 32-bit immediate offset. It's the 32-bit immediate jump instruction. Okay, so for the long jump, we can implement long jump using AUIPC and JALR. So these are more pseudo RISC-V pseudo instructions. So we learned of the J and JR. Also, you can easily find MB. MB means the move instruction. So it means that the data is moved from the source register to destination register. Okay, so actually MB is sent to the add I P5, so destination, source, and 0. Obviously, right? So actually the RISC-V hardware does not support MB, right? Because MB instruction can be easily implemented using add I. Okay, so but in the assembly code we can use MB. Okay, then assembler changes this MB instruction to add I. Not it's also the same. RISC-V hardware, RISC-V processor does not support not logical not instruction. So not is equivalent to XOR I and -1. Okay. No is the same. No means the no operation. So it means that one instruction is just executed, but this instruction does nothing. Okay. So this is the no. It's called the NOP or NOOP. So no operation. So we can also easily execute implement NOP not using add I 0, 0, 0. Obviously, right? So you can think why no is required. So sometimes it is required. Okay. So I'll explain later. But just remember that loop instruction does nothing, and then clock is just taken. So which means that the clock cycles are taken. So actually we can use the loop operator for taking clock cycles with no operation, nothing. And then also you can easily find, you can frequently find LI. So it's a low immediate, then very large number. Totally. It's equivalent to AUI and ADI. Okay. Then we can also find the call instruction RT. The call is the AUIPC and JALR. It's a very long jump. Okay. So these are RISC-V pseudo instructions. Okay. Okay, let's learn about the arrays. So actually, I already explained about the array data because I already explained about the array when I explained about the memory space or memory operands. Okay. So I briefly go through the slide. So each element of array has its own address, and then the address gap between the neighbor element is the same to the size of array element, right? And then using this characteristics, we can easily calculate the address. The address of the target elements in array. So this is the example. So if we want access the array 0, then we can just access this instruction using the what is this? Oh, it should be zero. It should be zero. Okay, so so in this example, S0 is the array base address. And then, so actually, in order to generate the address of data, then we need to use the 32-bit data, right? So actually, in order to generate the 32-bit data, then we need to use the LUI and add line because this is the large content. So actually, for this address is the 32-bit data. And then that's why we require LUI instruction. Okay. So using LUI and LI, we can store 32-bit address. So this is the base address of array. So S0, right? And then using the S0, we can calculate the target address of the first element. The first element is array 0, right? And then, so we can, so, and then so multiply by 2, because multiply by 2, so we can use the SLLI, okay? It just stored in the array 0. So SW here, it's the same, okay? So, as I explained, we can easily calculate the address of array elements, okay? Using the offset. So this is another example. And then actually we frequently use for loop to process array elements. Okay? So using the I, so this is the index. So index is the increment, and then using the increase the index number, then we can access the target element in array. So if we just handle array data, then we frequently use iterative loops in our high-level language code. Okay, so this is the example. Okay, and then ASCII code. So sometimes the program handles characters, okay, not numbers. Okay? But the computer processor just handle binary numbers, right? So that's why I explained about the label. So labels are text, right? But these labels are actually numbers, right? So it's translated into numbers. But sometimes we need to handle text data. So actually this text data is mapped to the numbers. So this this is called the ASCII code, right? Then it means that the characters can be mapped to some binary numbers. And then actually if we handle the characters, then it is handled like the arrays, right? Okay. So then array, and then I will just compare the arrays and pointers. So if we just use arrays, then we can just access array elements using the indexes of array, right? So we can just set I, the index of an array, and then by adjusting this value I, so we can just access the array element A0 or A1. But how about the pointer? As I mentioned, pointers are just addresses, okay? So which means that if we just know the base address of this array, then we can access each element in array using pointers. It means that using the addresses of target element directly, we can access it can access target elements in arrays. So this is the example. So this is the same function. So this function just initialize the elements in array using 0. Okay. So we can implement this function using the array index of the array, and then we can also implement this function using pointers, right? So in this example, the pointer variable is declared inside of the function, and then the pointer is the first value. The first value is the address of array 0, which means the base address, right? The base address of array, and then the pointer is less than that is actually the last element plus size of an element, right? Okay, it's less than the p, and then pointer is just increased. So in this example, because the pointer is declared as the pointer of integer, so which means that if we just increase the pointer by 1, so it means actually it is equivalent to the address of this p. Address is increased by size of integer, and then usually it's 4, right? So that's why the pointer is a little bit difficult, tricky, because Python does not have any Python variables do not have any size, okay? But the C has the many data types like integer, float, and then unsigned integer, long, double, something like that. And then actually the size of data, the size of data is determined by data type. So in this case, the pointer is just the address, but this is the integer type pointer. So E plus plus is equivalent. So pointer is increased by 1. So it means that the address is increased by also 4, the size of integer. Then let's compare the directly translated code. So I mentioned directly, okay? It's not optimized. So RISC-V assembly code are generated from this high-level C code directly. So let's see these two generated code. It's a little bit different, right? Right. So X5 is initialized using 0, and then it's calculated again and again. And then this is another example. So pointer version can be translated like this, and then in array version can be translated like this. The question, which one is better? So what does that mean? The better. Better means it should better for performance. Okay? So which one exhibits higher performance? How can we calculate? From chapter 1, execution time. Execution time is instruction IC, instruction count, CPI, PC. Okay? And then actually hardware is the same. So we can say that CPI and PC is same. Then which one is? So performance is determined by instruction count. Right. Then which one is better? Which one exhibit higher performance? So instruction count is large, then it means performance is low, right? Because the performance is the inverse of execution time. So which one is better? So it is determined by instruction count. So which one includes more instructions? This one, or two? Two, one. That's why one. Why? If we just check the number of instructions, so because of loop, okay? So, and let us assume that this loop is repeated n times, right? And then for this case, case one, this first instruction is executed, then 5 instructions are inside of loop. So actually the number of instructions is 1 plus 5 n. N is the iteration number. How about this code? So this code, then we can find 3 instructions out of loop, and then there are 3 instructions inside of loop. So it is number of instructions is equivalent to 3 plus 3 n. If n is large, then the number of instructions is determined by this one. Okay? So if n is large, then if n is large, this number is larger than this number. So which means that this loop has less instructions. So which means this code will be executed faster because number of instructions is smaller. Okay, so the pointer version is better. Then we need to use pointers instead of index. So why we use index? Because it's more convenient. The pointer is a little bit tricky, that I understand, because I understand that pointer is a little bit tricky. It's difficult to understand, actually. And then sometimes we can generate very critical bugs when if we use pointers. Okay? If we use pointers incorrectly, then we can actually generate critical bugs in our program. But we can observe that a pointer version is better. Then do we need to use pointers? Actually not. So because even though we use the array index, even though we use array data, then this compiled code, the compiled these 5 instructions are optimized by compilers. Okay, so actually compiler will generate this code, even though we use the array, and then if we just apply compilation optimization, okay, compile optimization techniques, then compiler will generate the code like this. So we don't need to worry about the optimized version of the this array indexing. Okay, so even though we use the array data format, then compiler will generate the optimized code. Okay. Okay, so now, so until here, until this point, we will learn about the assembly instructions. It's called the assembly instructions of RISC-V. Okay, so it is still stopped here. Right. So we can just represent these assembly instructions using characters, normal characters. Okay, and then the computer hardware cannot understand letters or normal characters. So which means the instructions needs to be translated into machine language. Okay? And then I mentioned that machine language includes digital data, and then digital data just includes zeros and ones. So another step. Another step for understanding hardware is to learn machine language. Okay, so until here, so we learned about the assembly instruction, and then we will learn how these assembly instructions are really translated into machine code, okay, or machine language. Okay, so it means like we learned about L5, 0, 0, 0. So this should be translated, 0, 0, 0, 1, 1, 1, 0, 0, something like this. So actually, each assembly instruction can be mapped to the machine language. Okay? Pseudo instruction is a little bit different because some pseudo instruction can be translated into true instruction. Okay, two real instruction, but real assembly instruction. One real assembly instruction is translated into one machine instruction. Okay, and let's see how the assembly instructions are translated into machine language. As I mentioned, computers only understand ones and zeros, right? And then which means that these instructions like add instructions need to be also translated into one and zeros. Okay, so characters need to be translated into zeros and ones. How? So in order to generate machine instruction, we need to set the size of a single instruction. So I already mentioned that size of a single instruction is 32 each 4 bytes, right? It's the size of normal single RISC-V instruction. And then some instructions has 2 bytes, it's the 16-bit. But in this course, we will not handle this reduced size instruction. Okay, so we set the size of a normal instruction as 32-bit. Okay, then we can use 32-bit binary data for representing assembly instructions. Okay, why we use the fixed size called simplicity favors regularity. So it means that if every instruction has same size, we can apply the simple translation rule. Okay, so simplicity favors regularity. So regularity, then the size is the same. And then we can categorize this translation rule as the 4 types. So there are 4 types of instruction format: the R type, I type, and then S type, and then U and J type. So let's see these different types of instructions. The first type is the R type instruction. So this R. So R represents actually register. And then firstly, we learn the arithmetic instruction like the add, right? Add RD, RS0, RS1. So this arithmetic instruction requires one destination register and then two source registers. So which means this arithmetic instruction requires three registers. Okay. So we can also find the many other instructions like the many other instructions that use three registers, right? Like the and or and then exclusive or is a logical instruction. Also, we can find the SLN, SRN, and SRA, the shift instructions. Okay? So actually, these instructions use three register operands, and then actually these instructions are called R-type instructions. Okay, so you can just understand like the R-type instructions just use three register operands. Okay, so and then RS1 and RS2 is source registers. RD is the destination register. Then the format is the same. So these instructions have the same format. So it requires three registers. Then how can we encode? How can we translate this instruction to the machine code? Okay, actually we can apply the same translation rule. So that's why it's categorized as R-type. Okay, assembly instructions also have the same type. It uses the three registers, and then the same type of instruction can be translated into the machine code with the same translation rule. Okay, and let's see how these R-type instructions are translated. So, for example, add RD, RS1, RS2. RS1, RS2. So you can find how the R-type instructions are translated. So in this example, you can find the bin number here. Okay, it's bin number 31, and then it's bin number 0. So and then I mentioned that the size of an instruction is the 32-bit. It has the bin number 31 to bin number 0, right? 0 to 31. So 32-bit, right? And then actually we represent the hardware data like here. So actually MSB has the larger number. Then LSB is the LSB. This is the MSB. The most significant bit, the least significant bit. And then LSB has the smaller number. Then MSB has the larger number. So then, in order to translate this instruction, then we need to translate the and. So we need to represent this machine code needed to represent and. Okay, first, and then destination register need to be translated. RS1 and RS2 also need to be translated. And then we learned that RISC-V has 32 general integer register, right? So actually this is the integer instruction. So which means RD can have register numbers from 0 to 31 because there are 32 registers, right? Right? And then in order to represent 0 to 31, we require how many bits? We need 5 bits, right? We can represent 0 to 31 using 5 bits, right? So which means, oh, RD, this is the, we can use the register number 0 to 31. So RD can be translated into 5-bit data. RS1 is the same, RS2 is the same. The RS1 can have the 0 to 31, RS2 can have from 0 to 31. Okay, so we can assign 5 bits for RD, RS1, RS2. So we need to use 15 bits for representing RD, RS1, and RS2. So we have a 31 minus 15, so we have a 16, right? So using the 16 bits, we can use 16 bits for representing and. So this is the R-type instruction. Okay, so firstly, OP. So OP occupies the first 7 bits, the lower 7 bits, and then RD is here. Okay, RD is here. And then after that, we can use the function 3. The function is called the function 3. So it occupies the 3 bits, and then RS1 is here, RS2 is here. It's a 5-bit, 5-bit. And then function 7 is here. So I just mentioned that, explained that. So in order to represent the RD and RS1 and RS2, we can use register numbers, right? So register number 0 to 31. And then it means we can use OP and then function 3 and then function 7 to represent and. Okay. But firstly, we use OP for classifying categories of instructions. Okay. So for example, we learned about the many different classes of instructions. So for example, arithmetic were load, store, branch, jump. Actually, these are categories of instructions. Okay. So firstly, using the OP code, this is called the OP code, OP code or operation code. So using the 7-bit OP code, we classify classes of instructions. And then using the function 3 and then function 7. So actually there are many instructions in the certain class of instructions. Then we just use function 3 and then function 7 for identifying a certain instruction like add. Okay, so this is the example. So you can find the add S2, S3, and S4. So another arithmetic instruction is the solve instruction. So these are R-type instructions, right? And then if you see this field value, so actually this example shows the add S2, S3, and S4, but these registers these registers exhibit ABI name, not the register numbers. So we need to translate these registers using register numbers. It's add X18, X19, X20. Okay, we can represent using the instruction using register numbers. And then not translate into machine language, we need to use register numbers, as I mentioned. So RD is 18, is RD, is RS1, each RS2, right? So RD is here. Oh, not this one. RD is here, 18, RS1, RS2. And then OP code of add is 51. Okay, so this is the arithmetic instruction. And then in order to represent add, function 3 is 0, and then function 7 is 0. So if we represent the 51 using binary number, this is the 0110011, right? And then 18 is the 10010, something like this. Okay, which means these numbers are represented as binary form, the binary data. Then if we just group 4 bits of binary, and then to generate hexadecimal digit. Okay, so this instruction, R-type instruction, is translated into each field of R-type machine instruction. Okay, and then these numbers need to be represented using binary number here. And then by grouping 4 bits, we can represent the binary instructions to hexadecimal number like this. So that's why you can find hexadecimal numbers in the dump file. Okay. So these instructions are translated like this. And then sum, this is another example. Sum is also the R-type instruction. Okay. So T0 is X5, T1 is X6, T2 is X7. So 5, 6, 7 is in RD, RS1, RS2 respectively. And then sum has also the same OP code because sum is the class of sum is same to the class of add. And then in order to represent sum, the function 3 is 0, function 7 is 32. So by combining these numbers, we can generate the binary numbers here. And then machine instruction is generated like this. Okay, these are R-type instructions. And then R-type format of RISC-V instructions. Okay. So actually, in the next class, we will learn other type of instruction like I-type, S-type, and there are many types. And then actually, you can find the summarized instruction format here. Okay, so you can find the category here, as you can see, load store is here, and then actually the format is in here. So you can also see the. Okay, any questions? Okay. Thank you for your attention. And see you in the next class.